All right, I've just got a short video, hopefully, here, where I want to look at an example in a couple of different ways. We're going to talk about how to apply these volumes of revolution formulas, disks, washers, shells, that kind of stuff, on some situations where our axis of revolution is not the x-axis or the y-axis. So this time, we're going to be taking a look at this one specifically, a vertical line at x equals -3. Let's go ahead and just draw our shape here, just so we can get some context. We've seen this example before. We've got this square root function. There, we've got y equals 2, which is going to be a nice horizontal line. We'll call it there. We're looking at this region inside. But now we're going to be revolving around this axis over here at x equals -3. So here's our square root function. Here's y equals 2. From 0 up to, I'll just say like up here, is 4. Let me extend this axis out a little bit. There we go. And we're going to revolve around this thing now. So what you'll notice is that we have a bunch of empty space in the middle here. When it creates this solid, it's going to look something like this. Where this hole goes straight down through here. All right, so we have to figure out how to create a volume formula for this using disks, washers, shells, and the like. So let's start off with the washer method. You're going to notice that we can't use disks, obviously, because we're not butting up against our axis of revolution, because we've just looked at the first quadrant. We're looking at the interval from 0 to 4. So when we use the washer method with these shifted axes, we've got a couple of different options here. Let me see if I can grab this picture, and I'll shrink it down for the next page. All right, cool. So when we're using washers and we're revolving around this line that's parallel to the y-axis, we're going to create some rectangular cross sections that go this way. We're going to have a delta y. So right off the bat, we're going to see that we need to translate this. So we're going to be looking at this function x equals y squared. And you notice our bottom function, or our leftmost function here, is actually x equals 0. So when we set up our washer, we're going to have something that looks like this. But we need to be a little bit careful when we draw our picture of our cross section with the faces. Because when we think about radii, our inner radius is clearly not 0, and maybe less clearly our outer radius is not y squared. What you'll notice is that y squared is this distance right here. Maybe I'll do this in blue. This distance is y squared, but what we want is this whole distance. So what we need to do is take this y squared, oh my gosh, I keep forgetting to take off my straight edge, and add a distance of 3 units. And similarly, our inner radius isn't 0, it's actually 3. So this is y squared plus 3, and this is 3. Now, our volume integral is going to be pi times the integral from 0 up to 2. Those are my y values that I'm integrating across. And I'm going to have my bigger radius squared. That's y squared plus 3 squared minus my smaller radius squared, 3 squared. This looks like the plus 3 isn't really going to do anything until we actually think for a second and notice that when we multiply this, we end up with y to the 4 plus 6y squared plus 9 minus 9 dy. And so we have pi times the integral from 0 to 2 of y to the 4 plus 6y squared dy. I'll let you finish this out and get our volume. So that's one way of doing things. Another way of doing things is to instead just shift everything. Let me get some nice straight lines here. Just shift everything so that we can... all right, let me start this over. I want to delete that. I want to delete this. All right, here we go. I'm going to take this picture, and I'm going to change it by shifting my function to the right 3 units. So suddenly, my function actually exists up here at 3. And instead of going up to 4, it's going to go up to 7. We still have this same y value at y equals 2. But now our axis of revolution is actually the horizontal line, the y-axis. I've just taken all of this and moved it up 3 units. That means that this function, the square root of x, actually becomes the square root of x minus 3. When we invert this, this becomes y squared equals x minus 3, and so x equals y squared plus 3. Hey, we might recognize that. You'll also notice that we've changed the y-axis now to be this vertical line at 3. Our interval changes from 3 to 7. So suddenly, when we take a look at our volume, we still end up with the same volume integral. Our limits of integration didn't change. Those are still going from 0 to 2. We haven't shifted things up or down. We've shifted things to the right. Our outer function is this one right here. It's this square root function, which we're writing as y squared plus 3. And our inner function is this one right here. So we still have 3 squared. So notice this is the exact same thing. There's no difference, but you can think about it a little bit differently by just applying these transformations of functions to shift to the left or right here. All right, let's think about this using shells. So same region, same thing that we've got. We'll put this in the corner, make it a little smaller. And now what we'll do is think about some shells. These are going to be oriented this way with a delta x. So we need to think about our cylinder. When we cut this thing open, we're going to get a nice rectangle where the height of this is going to be the height of our bar here, which is just going to be 2 minus the square root of x. And the width of our rectangle is going to be the circumference, which is going to include a radius. But now notice the radius of our cylinder starts all the way down here at -3 and goes up to this x value. So this is really x plus 3. So we have our circumference, 2 pi times the radius, 2 pi times x plus 3. So now we can set up our volume. This is 2 pi times the integral from 0 to 4 of our radius, x plus 3, times our height, 2 minus root x dx. You can multiply all this out, and we end up with 2 pi times the integral from 0 to 4 of, we're going to get a 6, we're going to get a minus 3 root x, we're going to get a plus 2x, and we're going to get a minus x to the 3 halves. And you could go ahead and integrate that, and it's not too bad to do. In the exact same way, though, as we did before, we can shift this thing. So let's take a look at this function when we shift it. Oops. Let me put it here so I can grab it again, and we'll scale this thing down. And now we're going to shift everything to the right. So I'm going to draw my axes here. But now my function gets shifted to the right again. Oops. I got to keep taking off this straight line shape. I still have this same horizontal line at y equals 2, but now we've got this line here at 3. And notice we go up to 7 now. Because remember, we shifted our interval from 0 to 4 up to 3 to 7 by just bumping things up to our axis. So now we can revolve around this one. Now, when we do that, we have this shell here. Our function changed. Remember now, it's the square root of x minus 3. And our interval changed. It's 3 to 7. So we can think about our cylinder. We're going to have this cylinder that when we cut it open, we get a rectangle. The height is 2 minus our square root function, which is now 2 minus the square root of x minus 3 with our horizontal shift involved. Our radius now, though, is just x, which is kind of nice because it's just measuring the distance from our rectangle to our y-axis. So on the bottom of our rectangle, we have 2 pi x, kind of like we're used to at this point. And that means our volume integral is going to be 2 pi times the integral of x times our height, 2 minus root x minus 3 dx. And our limits of integration, notice they change. We go from 3 to 7 now. Let me write this a little bit cleaner, a little bit nicer. That's a 7. There we go. And we'll just do some distributive property. This is 2x minus x root x minus 3. And there are other things that we can do with this. And this is our integration. Notice that this is a little bit of a more annoying integral to deal with. We can split things up and do some u substitution, and it'll work out okay. But this is kind of a trickier one in this case. So maybe it's easier to do this version of it. But we've got either of these paradigms. So all this to say, here's our summary. When you're looking at something where the axis isn't necessarily the horizontal x-axis or the vertical y-axis, you can always try to shift your functions using transformations, shifts left and right, up or down, to center everything back to the x or y-axis. So if you have something where your axis of revolution is y equals -2. It's 2 units underneath. You can shift everything up 2 units if you'd like. Notice that with shells, that's going to change your limits of integration as well, not just the functions. The other thing you can do is you can add length to the radius. With shells, the length gets added right here. That's our radius. Whereas with washers, it gets added to both of these radii before you square them. So just keep an eye on that. It shouldn't be a huge deal, but these typically end up being a little bit more involved of problems because there's a little bit more of the visualization that we have to figure out. It's really easy to lose this extra length on a radius. I find people forget about it a lot in washers where they'll add it to one radius and not another or something like that. Or they'll take like a disc and forget to turn it into a washer when the radius is moved away. So just be careful. Take a look through this again, though, if you want. See if you can work these problems out. Make sure that all of these volumes that we found match up because they are the same shape. But we have 4 different methods for doing them now.